I hope you enjoyed the event today and that you learn a lot, both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
Yeah, hello, welcome back everyone. So our speaker today is Mats Steinweg. Mats is working in the robotics and perception group at the University of Zurich. And his research interests are centered around motion planning and control for autonomous mobile robots. And so this is what we will hear from him today. So Mats, we are looking forward to your talk.
Okay, can everybody see my screen and hear me?
Looks good.
Great. Okay, yeah, thank you very much again for the invitation and the introduction. And today I'd like to talk to you a bit about reinforcement learning in the context of research on autonomous drones and more specifically the task of drone racing. This is research that I've worked on as part of my master thesis here at the Robotics and Perception Group. And I'd like to start with a little bit of an introduction about autonomous drones in general, and then focus a bit more specifically on the work of my thesis. So let's start with the introduction about autonomous drones in general. And the broader research field that most of the research performed at the Robotics and Perception Group belongs to is known as agile quadrotor flight. And in this research, we focus on quadrotors that are mostly equipped with cameras in order to perceive the world. And the idea is that the quadrotors are able to perform all the computations fully on board. So they're able to navigate autonomously in even unstructured environments. And the focus of this research is to develop algorithms that allow the quadrotors to fly as fast as possible and also perform very aggressive maneuvers. This is very important for a large number of applications in the real world. Examples include the inspection of power lines and also the delivery of packages or search and rescue scenarios. If we take the example of a search and rescue scenarios, an autonomous quadrotor that can fly very fast allows you to do two things. You can minimize the time until you potentially discover a victim, and you can further increase the area that you can cover with your autonomous quadrotor within the limited battery life. All these actually pose very fundamental challenges to robotics algorithms in mainly perception, planning, and control. And to push the performance of these algorithms and develop new state-of-the-art algorithms, a very prominent example that's used in research are challenges that are organized at international research conferences. And this is where the autonomous drone racing part comes into play. Autonomous drone racing competitions have been organized at international research conferences since the IROS conference in 2016. Since then, these competitions have become regular events. And in 2019, autonomous drone racing competitions were even brought to audiences beyond the research world at the Alpha Pilot Challenge that focuses on pushing the performance of autonomous quadrotors in terms of speed and also comparing the performance of autonomous quadrotors to quadrotors flown by expert human pilots. And although at the moment, the gap between the performance of autonomous quadrotors and quadrotors flown by expert human pilots is still pretty large, the ultimate goal of all these challenges is to eventually develop these quadrotors that will allow us to beat expert human pilots on complex three-dimensional racetracks. To give you a better idea of what the drone racing setup looks like, I'd like to show you a video of the contribution of the Robotics and Perception Group to this Alpha Pilot Challenge in 2019. What we see here is the performance at the challenge of the Robotics and Perception Group. And the quadrotor that we see here, this video will just keep running, actually performs all the computations required fully on board, and there is no human involved at all. So the moment this drone starts flying, no human is involved. And the quadrotor, as we see here, achieves top speeds of up to 8 meters per second and performs quite aggressive maneuvers. let's actually have a look at what these computations are that are required in order to allow the quadrotor to fly autonomously on this racetrack. To do this, I'd like to show you a simplified overview of the system that was actually developed by the robotics and perception group here. And this system consists of 6 main components. The first one that we already see here is the sensor interface. As I said, the quadrotors are usually equipped with cameras to perceive the world around them, and as well as inertial measurement units. The information is then used in a first processing step in the perception module of the system that mostly does 2 things. First, there is a gate detection component that uses the camera images to usually detect the corners of the gates. And then there's a visual inertial odometry pipeline that provides us with information about the motion of the platform. This information is then used in the state estimation module of the system. Here, we fuse the information about the gate corners as well as the odometry data to actually compute a consistent global map of the gate layout as well as a state of the quadrotor. So we know where is our drone, how is it oriented in the world, and where is it relative to the gates. The next step is the path planning step that takes this information and actually plans the trajectory of the quadrotor that we want to execute. This is then outputted in the form of a reference trajectory that is fed to the control component of the pipeline. In this control step, the reference trajectory is used to compute the actual commands of the rotor of the quadrotor platform that have to be applied in order to follow this trajectory as accurately as possible. The computed control commands are then passed to the drone interface. This should give you a rough overview of all the required computations that are happening on board an autonomous quadrotor. In my work, I focused on the path planning step of this pipeline, meaning that we take information about the layout of the gates as well as the state of the quadrotor in order to plan a path for the task of drone racing. As we see here, there is a lot of other computations involved, and in order to focus on a single task in isolation, the uncertainties that are introduced by the other components of the system make this very difficult. So what we do in order to isolate this task, we actually perform the entire project and all the experiments in a simulation environment. Specifically, we use here the Flightmare simulator that was developed by the Robotics and Perception Group and presented at the conference on robot learning last year. This simulator was specifically designed for quadrotor control with reinforcement learning. And we see here on the right a rough overview of the architecture of this simulator. So under the hood, we have a dynamic simulation that is implemented in C++ that allows us to accurately model the dynamics of the platform, as well as simulate this, the quadrotor platform very fast. In order to apply reinforcement learning, we then have a connection to Python in the form of an OpenAI gym environment. So we can just plug in existing implementations of algorithms for reinforcement learning here. The third component is a rendering engine in Unity, which would either allow you to perform vision-based algorithms or to just look at your drone, which we'll actually see later as well. So in summary, using a simulation environment allows you to isolate a single task from this very complex pipeline. And also you don't have to perform experiments using a very expensive physical quadrotor platform. Before we actually look at how we use reinforcement learning, I'd like to define this task of path planning that we focus on here in a little more detail. Because we're looking at a racing task, the concrete task that we solve here is known as time optimal trajectory. And the goal is to compute a trajectory through multiple gates on the track, given prior knowledge of this track layout. So we don't do anything during flight, but instead we perform the computation of this optimal trajectory that we want to follow before we start our flight. And to give you an idea of the kinds of tracks that we want to compute these trajectories for, we see here on the right an illustration from a track that is taken from the Game of Drones challenge that was organized at the NeurIPS conference in 2019. This track consists of 21 static and square gates that are oriented in three-dimensional space, and the total length of the track is around 330 meters. In general, we focus on fully three-dimensional tracks in drone racing. So this is just one example of a large number of possible tracks. And computing a time-optimal trajectory for this kind of track raises a number of very interesting research challenges. And I'd mainly like to focus on three of these challenges here. The first is that we actually have to account for the dynamics of the quadrotor platform when we compute this trajectory. So we have to take into account the nonlinear dynamics that govern the motion of the platform, as well as the constraints of the actuators that we can use in the form of the four motors that actually power the platform. And the second challenge is related to the scalability of the algorithms, because we see here one example, as I mentioned, a couple of 100 meters, but we also want to be able to compute trajectories for tracks that are just, let's say, 50 meters and one or two gates, or massive tracks with a large number of gates. And a third aspect is the robustness of the algorithms, because a very popular task formulation in drone racing actually provides you not with the exact location of the gates, but only with approximate gate locations. So when you develop your algorithm, you don't know exactly where the gates will be. You just know this with a given uncertainty. And then before you start your race, you have to adapt to the actual track layout. We'll see this later as well. So let's now have a look at how we can actually apply reinforcement learning to this kind of task. And the potential for path planning of reinforcement learning can be summarized using 3 bullet points. The first benefit of reinforcement learning that I see for the task of path planning is that we can use very accurate, high fidelity simulators in sort of this black box fashion, because we can use it for the data collection in a model-free setting and benefit from more and more accurate simulators. This essentially means that a reinforcement learning based method becomes even stronger with progress in accurate simulators for quadrotors as well. And there is a lot of effort going into more accurate simulators. The second benefit of reinforcement learning is that if we apply this to a simulation environment, we can speed up the training process of the agent considerably by just parallelizing the dynamic simulation and using a large number of quadrotors in parallel to collect the data that we use to train our policy. The third aspect is related to the deep neural networks that we actually use to represent our policies, because the generalization capabilities allow us to actually learn skills that can be applied to similar tasks. So we're not restricted to solving one specific problem, but we can solve a large class of problems using reinforcement learning. Before we focus on the specific formulation of reinforcement learning or the connection of reinforcement learning and drone racing, I'd just like to briefly introduce the general framework and the notation. So what we see here are the two main interacting entities, the agent and the environment. And the agent interacts with the environment by applying actions and then, as a result, collecting a reward and observing the state. And this reward that the agent observes indicates the goodness of the action that was applied to the environment. In the equation at the bottom, we see the expression for the optimal policy, which is here denoted as pi theta star. And as we see, this optimal policy maximizes the expected value of the discounted future reward. So the reward function plays a very central, is a very central component of the formulation of our task. So let's now finally have a look at how we define this reward function for the task of drone racing. The task of drone racing itself has a very intuitive reward in the form of the final lap time. Because if our quadrotor arrives at the last gate and has successfully completed the entire racetrack, this captures the full complexity of the task. But the problem with the final lap time as the reward is that we can only compute it at the end of each trajectory, which makes it a very sparse reward signal, which is problematic for current reinforcement learning algorithms. So one approach that is frequently used in the literature in these sparse reward scenarios is called reward shaping. And this refers to the design of a reward function that closely approximates the intuitive reward here, but which we can compute at every time step and thus provide the agent with feedback on a regular basis. And the specific reward that we use in this project is a path projection reward that has already been used frequently by other works for racing tasks, for example, in car racing. And we see an illustration of this reward function here on the right, where we have two gates that are projected to the horizontal plane. And we see the representation of our reference path in the form of straight line segments that connect the centers of these gates. So what we can do at every point in time, we can take the three-dimensional position of the quadrotor and project the position onto these line segments. And then if we compare the progress along the projected progress along these line segments to the previous time step, we get a reward signal that if we optimize this over a long horizon, actually closely approximates the lap time. We see the specific formulation of this reward, which is very simple here at the bottom left. So for a projected position on the center line, denoted here as PC, we pass this to a function S that maps this to the progress we've already made along this reference path. And then we just compare it to the previous time step, which then gives us a scalar reward signal that we can compute at every time step, which can easily be optimized by existing reinforcement learning algorithms. So now that we've talked about the reward function, let's have a look at two other relevant components for reinforcement learning, the observation and the action space. The observation space in the reinforcement learning problem essentially defines the information that we provide our agent with in order to solve the task. And the observation space that we use in this problem, we can see here in the box at the top, consists of two main components. We have the first component that captures information about the state of the quadrotor, which we denote or which we use here in the form of the velocity and the acceleration, the orientation of the quadrotor in the world frame, as well as the body rates or the angular velocities. And then the second component of the observation space is related to information about the track. And we provide this information in the form of the relative pose between the quadrotor and the next two gates in this case. So the information that we have here only provides limited information about the track. And we'll see that this is actually sufficient. The observation vector is then passed to the network, which in this case is a conventional multi-layer perceptron, which consists of two layers with 120 units each, so a rather simple architecture. And what we see here is that we don't leverage temporal information or anything. We only provide information about a single time step that is passed to the network. And the output of this network is directly mapped to the thrust commands of the four rotors of the platform. And this allows us to actually incorporate constraints that model the input constraints of a physical quadrotor platform very accurately. So with this information about the reward function, as well as the observation and action space, we can finally look at the actual training of the agent. And the agent that we use in this work is based on the popular proximal policy optimization algorithm, which performs the training in alternating steps of data collection and policy updates. And in order to both speed up the data collection and also diversify the data that we collect, we use 100 quadrotors in parallel for the data collection, and further leverage a distributed initialization scheme that allows us to train independently of the size of the track. And we see this distributed initialization strategy here in the illustration on the right. This is the start of an episode, and the purple dots that we can see here correspond to the initial position of these 100 quadrotors that we use in parallel. So what we see is we initialize the quadrotors in the center of all the path segments, as well as at the start position. And by using this distributed scheme, we immediately expose the agent to all the gate configurations that are present on the track, which allows us to accelerate the learning process. For each update step, we then collect trajectories of a total of 500 seconds of flight time. This means 100 quadrotors, 500 seconds, that's 5 seconds per quadrotor. And we do this at a sampling frequency of 50 Hertz, which means that for each quadrotor, we collect 250 environment interactions for each update step. And a typical training then requires around 1,400 hours of flight time, which of course would not be feasible with a simulator that actually runs in real time. But because of this parallel sampling, our simulator has a significant speed up factor so that we can perform a training within 2 to 3 hours of wall clock time. I'd now like to show you a video that illustrates the entire training process of an agent that starts with absolutely no knowledge about the task. So what we see in the beginning, the episodes end rather quickly with a crash before the agent actually captures this concept of making progress along the path and passing the gates, which happens faster for some path segments than others, especially if we look at the upper right corner with this sharp turn. We can see that it takes quite a large number of update steps until the shape of the trajectory is actually optimized for this sharp turn. When we arrive at the final policy here, what we can clearly observe is that straight path segments are used for acceleration, and then the quadrotor decelerates quite abruptly prior to the sharp turns of the track in order to exploit the track layout to optimize the lap time. With this insight about the training process, we can now have a look at the experimental results. And we structure the experimental study into 3 groups of experiments. In the first group of experiments, we focus on racing on deterministic tracks, meaning that the entire track layout is perfectly known in advance. So there is only a single track that we want to race on, and we want to answer the research question of how this lap time that we can achieve compares to traditional non-learning based methods. In the second group of experiments, we'll focus on the robustness property of the reinforcement learning method. I mentioned this earlier, and here we focus on racing on uncertain tracks. So tracks where we don't really know where the gates will be exactly, but only know this right before we start the flight to actually investigate how robust the reinforcement learning method is. And this study on the robustness property is further extended in the third set of experiments, where we remove entirely the assumption that we train on a single track or variants of a single track, but instead we just randomly generate the tracks during training of the agent in order to see if it's actually possible to train an agent to fly on unseen tracks with just information about a limited number of future gates. So let's have a look at the results of the first experiment. And what we see here is the track that we already saw in the beginning, which we refer to as the air sim track. And what we see here is the fastest trajectory for this track generated by our reinforcement learning agent. And in the table at the bottom left, we see two baseline results along with the lab time performance achieved by the reinforcement learning method. And let me briefly talk about these baselines. The first, the polynomial method, is a trajectory generation method that has been around in robotics for quite a long time, and that is particularly popular for generating smooth trajectories. So this is a baseline that is not optimized for fast flight, rather to be taken as a conservative baseline here. And then the second method, CPC, is an approach developed by the robotics and perception group that solves the trajectory generation task by defining a nonlinear optimization problem for this specific track. And in this scenario, the CPC performance can be thought of as like the theoretical upper limit that you can achieve with the rotor configuration on this specific track layout. So what we can observe here, if we look at the lab times, is that the reinforcement learning agent performs somewhere in the 4% bound of the theoretical upper limit achieved by the optimization-based method. And this is actually something that we can also see for other tracks. We see here two other tracks that we use for the evaluation of the method. On the left, one track that was used in the Alpha Pilot Challenge, which features less variation in the vertical dimension than the previous track, but has more challenging path segments because there's sharper turns present on this track. And here we see a very similar tendency in the lab time results. So the conservative baseline performs considerably worse, and the reinforcement learning method gets pretty close to the optimization-based method. Let me just see, there seems to be a question here. Okay, I think this question is not very relevant now, sorry. And then we see the second track here, which we refer to as the split S track. This track is specifically designed for indoor experiments with physical quadrotors in the motion capture arena, for example. And we call it the split S track because of these two vertically stacked gates there that look like the upper half of an S. And for this track, we see as well, although the scale is considerably smaller and the speed at which the quadrotor flies is a lot lower, but the lab time results are very similar. So the performance is still within 5% of the optimization-based method, but doesn't quite get there. So with this insight about the lab time performance in the deterministic setting, we can look at another property of path planning algorithms, which is the computation time. So in this setting where we have an entire racetrack and we want to pre-compute the time optimal path, it is very interesting to know how long it takes to compute this trajectory, because this essentially defines the areas of application where you can use these algorithms. And in this experiment, we compare the computation time for CPC, which is a member of optimization-based methods, and then the reinforcement learning method. And we do this by comparing the computation time for the three tracks that we saw on the previous slides, as well as randomly generated tracks of different complexities. And we can look at the results here on the right. We have on the x-axis the length of the track in meters, and then on the y-axis, the computation time in hours. And what we can clearly see in this table is that the computation time for the optimization-based method increases drastically with the size of the track. This is very intuitive because the optimization problem is set up for a specific track layout. And so the size of this optimization problem increases with the size of the track. This is not necessarily true for the reinforcement learning method, because as we saw earlier, we can just scatter these parallel actors across the racetrack and thus cover the entire racetrack independent of its size from the beginning of the training. And so we're actually able to train our agent independent of the size of the track here, which we see with the in green here. And this highlights one of the main benefits of using a learning-based method for the task of path planning. Although we don't quite achieve the lab time performance, the computation time doesn't scale with the length of the track as it does for optimization-based methods. So these are the insights that I wanted to share about the first set of experiments. So we can now move on to the second set, in which we focus on uncertain tracks. And before we talk about before we look at the results, I'd like to specify the type of uncertainty that we use here in a little more detail. And what we see here in the illustration on the right is the track from the Alpha Pilot Challenge that we saw earlier. And in black, we see the nominal gate locations that are provided. And then we're provided for each gate with a gate-specific uncertainty bound on the position of the center in the three-dimensional space. So this means that the center of each of these gates can be moved arbitrarily within the respective cube. And furthermore, the orientation of the gate can also change in the horizontal plane by up to 45 degrees. And the idea of this experiment is to see if we can actually train a policy that can robustly generate trajectories that don't crash for all possible versions of the track that we can create using these gate-specific uncertainties. And to show you in a little more detail what this means, I'd like to show you a video that illustrates the different gate layouts that these uncertainty bounds can actually result in. And specifically, if we focus on the gate at the top right, we see that this orientation changes pretty drastically. So in order to be able to compute trajectories for all possible versions of these tracks, we actually have to learn transferable skills based on the information about future gates. So let's have a look at the results here. And the training is performed by just randomly sampling the actual version of the track that is used during training. So we train on a large number of these tracks in total. And the evaluation is then performed on a test set of 1,000 of these randomly generated tracks. And we report the results in the form of the number of crashes for different difficulty levels. And the difficulty level here corresponds to the percentage of the maximum displacement. So we saw on the previous slide that this was up to 7 meters, which is what we see here as the difficulty level of 1. And for this difficulty level, we observe a total of 25 crashes for these 1,000 tracks. But if we reduce this complexity that we use during evaluation, which means that we trained on more complex tracks than we evaluated, corresponding to a rather conservative setup, then we actually reduce the number of crashes to 0, which are great results here. And the other metric that we can look at is the lab time that this policy achieves on the nominal version of the track, meaning the original track without any of the uncertainties. And we can compare this to the results of the previous experiment, where the agent was only trained on one version of the track without any of the uncertainties. And if we compare the lab times here, we can see that the performance drops from 8.14 to 8.32 seconds. And this actually highlights one of the main benefits of the reinforcement learning approach. So we have a reduction in the lab time performance by around 0.2 seconds here, but we gain robustness to a very large number of different tracks. So we don't have to retrain our policy. We can just generate trajectories that fly very fast without crashing for a very large number of these tracks. And to illustrate the complexity of this task in a little more detail, I'd like to show you a video that contains 100 successful trajectories that were generated by the same policy for different versions of the track. So you see all the quadrotors start at the same position, but then each of these quadrotors flies on a different version of this track. We don't show the gates here because otherwise you'd only see gates basically, but this should illustrate how or how wide the variety is of these tracks that we actually train on. And in the third experiment, we wanted to investigate if it's possible to take this even further. Can we use this robustness property in even more complex scenarios? So instead of randomly generating versions of one track by disturbing the gates, we just generated all the tracks that we used during training randomly. And we trained the policy by adaptively making these tracks more complex. So we started with tracks that were basically only small variations from straight line segments. And once the agent had actually learned to fly on these simple tracks, we made the tracks more complex and more complex until we actually arrived at the distribution of tracks that we wanted to train on. And we report the results here in the form of the success ratio, meaning the number or the percentage of the tracks that we can fly on from the start to the goal without any crashes with the gates. And we achieve here a success ratio of 97.4%, again, evaluated on a test set of 1,000 completely randomly generated tracks. And to illustrate this in more detail, I'd like to show you another video. So what we see here are 100 gates, and these 100 gates belong to 10 different tracks that we generated randomly. And all of these tracks have the same start position. So if you look here in the center of the screen, you see the red quadrotor. So this is where 10 quadrotors will now start to fly. And these these trajectories are all generated by the same policy. So let me see. Oh, there we go. So all these quadrotors fly on totally different tracks, but the trajectories are all generated by one policy that was trained by randomly sampling the tracks during training. And what we've looked at so far is the performance in terms of the success ratio. But of course, it's also interesting to look at how this policy that's trained on the random tracks performs in terms of the lab time performance. And in order to compare this, we picked 3 of the tracks from the evaluation set at random and compared the lab time performance on these tracks to policies or to trajectories that were actually generated specifically for these tracks. So what we see here in the table at the top left, the performance on these tracks achieved by CPC, so the optimization method, by a single track policy, the policy that was trained specifically for this track, and the random track policy that was trained on a large number of tracks. And what we can observe is that from the second to the third row, the lab time drops by around 20%. And this actually becomes clear as well if we look at the shape of the trajectories. So what we see here is 2 trajectories, one flown by a single track and one by the random track policy, projected to the horizontal plane. And if we zoom in here, we see that the single track policy, which is displayed in blue, exploits the track layout in order to optimize the lab time, while the trajectory that is generated by the random track policy is clearly suboptimal if we want to minimize the lab time performance. So the results of the third experiment indicate that it is actually possible to train a policy on a large class of tracks by randomly generating these tracks in terms of the success ratio, but there is certain trade-off when it comes to the lab time performance. So you always have to think about how much generalization to unseen tracks do I want and how fast does the trajectory need to be. So this is everything that I wanted to share about the experimental study. And this actually brings me to the conclusion. And I'd like to summarize the contributions and the achievement of this project. So what we present in this project is the first learning-based approach for near-time optimal quadrotor trajectory generation. And in order to develop this method, we implemented a versatile formulation of the task of drone racing in the reinforcement learning framework that allows us to focus on many aspects of the drone racing task, which means we can race on deterministic, unseen, and even randomly generated tracks. And the reinforcement learning method displays great robustness to uncertainties in the track layout, meaning that we can generalize to a large number of tracks, and also features very attractive computation times if we compare it to optimization-based methods and talk about very large scale environments. For the extension of this project and future work along this line of research, there are sort of two orthogonal directions if we want to go towards real-world deployment. The first is that we need to integrate the reinforcement learning-based path planner with the other components of the system that we saw in the beginning. So we have to take into account the uncertainties in the estimates provided by the other components of the system in order to integrate the reinforcement learning-based path planner. The other orthogonal direction would be to actually reformulate the drone racing task in the reinforcement learning context by taking into account more components of the system. So one approach could, for example, be that we include the perception module in the reinforcement learning formulation, which would then be learning from pixels. So we could take visual input from the cameras and map this to a trajectory. Or if we instead include the control component, we could, for example, formulate a reinforcement learning problem in which the quadrotor is tasked to generate the commands that are then applied to the physical quadrotor, which would then be end-to-end control using reinforcement learning. So these are all very exciting avenues for future research, and I hope we'll be able to share something with you. And this actually brings me to the end of my talk. The work that I presented today is joint work with Yunlong Song, Elia Kaufmann, and Professor Davide Scaramuzza. And I hope I gave you an idea of what reinforcement learning can do in the world of autonomous drones. And if you're interested in more details, make sure to check out the paper as well as the video on YouTube. And if you have further questions, I'm happy to answer them right now. Thank you very much.
Thanks a lot, Mats. For a really fascinating talk, really nice work. And we have some time for questions. So everyone, please, if you have a question, write them in the Q&A tab.
Yeah, there were a couple of questions here during the talk.
Actually, maybe I start with a question. If you zoom out a little bit, because you see, I said in the beginning, it's still very far from human performance, I think.
Yeah.
What's the main milestones still missing there? Is this just what you said, or is there some more general things which are missing?
I mean, as we saw in the beginning, there is just a lot of different components involved there, and at the moment, the progress is usually on single components of the pipeline, and it's really hard to integrate them together in order to form a system that's more unified in the design. So what I said in the end, include the perception and or integrate the perception with the path planning. So I think there is progress required on all of these components, and actually in order to actually arrive at the human performance.
Okay, cool. But it seems to be going fast. I mean, that's already a lot of progress compared to the last status I saw.
Yeah, that's definitely true. So there is one question that if we replace the line segments of the planned path with something smooth, like a Bezier curve or polynomials. Let me just quickly jump to that slide. So we have this here, I think. Yeah, so exactly what we use here is straight line segments in order to connect the gate centers, which is a very minimal representation of the reference path because it doesn't really provide a lot of information about the shape of the trajectory. But because this, because it allows us to formulate a very minimal reward, and also because this reward is optimize over a very long horizon, we found it to be sufficient to use this minimal representation. We actually implemented the other options in the beginning where we used the output of optimization-based methods as the reference path, but we found it simpler to just use the straight line segments, because what this does mainly is it allows you to define new tracks by just defining the positions of the gates, and then you can just compute the reference path by connecting the gate centers. So I hope this answered this question. Does performance suffer when you use a model generating the simulator on a physical track? Actually, in this project, we did not focus on the real world deployment. So we focused entirely on simulation. And so this is actually something that we have to explore in future work, how the discrepancy between a model in a simulator and the real world platform actually impacts the performance of a reinforcement learning based method. But it's definitely expected that in the current version, because we didn't take into account these uncertainties that are introduced by real world dynamics, actually affects the performance. Have you tried to estimate and regulate risk of a crash somehow? Risk aversion or value at risk approach? So we haven't implemented anything in terms of risk averse reinforcement learning. What we experimented with, let me just jump to that slide, is another reward component that, because this progress reward that we use doesn't include any information about where you pass the gates. And because you optimize the lab time, it's quite likely that you actually pass the gates very close to the borders, because this is what usually optimizes the shape of the trajectory. But what we see here is a reward that actually pulls the quadrotor towards the center of the gate when it's flying through the gate. So it maximizes the safety margin to the border of the gate. And we do this by just providing a negative reward for these high risk regions that we see here close to the borders of the gates. Then we see what type of optimization method is CPC. CPC is not really a specific optimization-based method. It's an approach for generating time optimal trajectories by optimizing the shape of the trajectory jointly with the allocation of the traversals of individual gates to time. So in the end, it's just a formulation of a nonlinear optimization problem. I think that as a high-level summary, that's okay. From the inside that a policy train on a specific tracks outperform a policy train on random tracks for the specific track, to look into fine-tuning online adaptation of the policy. No, at the moment, not. This could actually be something that you could explore in future work. We just focused on the performance in this setting where you train from scratch on randomly generated tracks, because for now, this was the most interesting for us to actually explore the limitations of the approach in this or in this configuration. And this was actually very interesting for us to see that there is, that you actually hit the ceiling if you have very complex tracks that you randomly generate. You cannot reduce the crash ratio to 0, for example. And then there's one, have you ever tried to achieve a robust policy with a maximum speed of over 10 meters per second? Seems that in this generation of drone with solve the trade-off between reliability and agility of flight, which is the maximum. Yeah, so I think here we have to differentiate between the quadrotors that actually, like actual real world quadrotors that like we saw in the beginning. So here it is true that if we jump to this slide, oh no, it was, sorry, here it is. So here the maximum speed that was achieved is actually 8 meters per second. And the main limiting factor here is actually the state estimation part, because if you go for higher speeds, you get a substantial drift and a larger error in the estimation of the state. So you get inaccuracies in the information about where your drone is, and this makes it very complicated or impossible to control your drone anymore. And for the simulation environment, that's a bit difficult, or that's a bit different, because here we're not constrained by any of the uncertainties that arise in real world scenarios. So the trajectories that we generate here are actually very fast. So here we're only limited by the input constraints of the platform, and actually achieve speeds of up to 35 meters per second, which is something that human pilots can achieve sometimes, but that's definitely nothing that autonomous drones can achieve at the moment. Yeah, so I think that's actually all the questions that I have here in the chat.
I think we can close it here. Thanks again, Mats, for this fascinating work that you showed us. Yeah, I think so. That's it. So actually, you will also receive a little present from us. It's a tradition we have for the speakers. Will be a virtual one.
Thank you very much.
Yeah, thanks for coming, and thanks everybody for listening, for joining us today. Hope you liked it. Yeah, so that's it. Have a nice evening, everyone, and see you next time. Bye-bye.
Thank you very much. Goodbye.